We're starting, yeah. Okay. I need someone who can hold a 10 Newton weight in one hand. Okay, come on up, Paul. Hold this 10 Newton weight in one hand. Stand over here. Well, are you left-handed or right-handed? Okay, then hold it in your left hand. Okay, look at that. Is he having any trouble holding this 10 Newton weight in his left hand?
No.
Of course not. Tell me, could I make it so that it was really hard for him to hold this 10 Newton weight in his left hand?
Yeah.
Sure I can. Let me show you. Keep that hand out.
Oh boy.
Okay, go for it. Here we go. 1, 2, 3. Oh my gosh, you're such a man. Okay, all right. Well, here, I gotta get the stupid phone. Stay right there.
What a man.
That's what you gotta have every night, bro.
Oh, I got you.
Whoa. Yes.
You got it.
Okay, where should I
We're
say
gonna
that?
cut that out of the video, right?
Oh, okay, I'll put it down. Okay, great.
I'm gonna look for that video.
No, it's fine. Justin Hamill, go downstairs to Mr. Davis's room. Do you know where he is?
Yeah.
He says there's a coach from Redlands who wants to talk to you.
Oh.
That might mean a free education for you, so don't miss it. Also, people like Redlands. So are you really that strong? Here, like hold the end and just. I mean,
Extend his arm out.
Watch this.
Have him extend his arm
No,
out.
he's good. Okay, you see that? Do you see how it? And of course, now he's able to do it. But do you see how it rotates? I just want you to see that what's happening here isn't force. If the force was too much, the whole thing would just fall together. But what is it about this that's making it hard for him to hold it? You can see he's shaking. Well, what's making it so hard for him to hold? Torque. Okay, torque, yeah. But how have I changed the scenario?
Made it long.
Yeah, I made it longer. I put the mass really, really far from him. You see, it's the same force that's being exerted, but the problem is this force is acting at this really far distance, which makes it really hard for him to hold it. But I want to say again, it's not that the weight is too much, it's the fact that it wants to rotate. It wants to rotate this assembly, you know? And so that gets us to the thing we're about to learn, not force, but rotational force, or twisting force. Thanks a lot, Paul. Yeah, give him a hand. Strong guy. Almost ruined my demo by being too strong. I gotta be careful about who I choose next time. Okay, so this gets us to this idea of torque. Okay? And torque is, for the layman, it's many things. It's turning force. Or another synonym for it would be twisting force. What it does is it tends, unlike a normal force, which will tend to change the motion of something, a force changes the motion, changes the velocity of things. A torque will change the rotational motion of things. It changes the rotational motion of things. And I just want to keep emphasizing the point that this thing started off with no rotation. And then when I put the mass on, it wanted to start rotating out of his hand. In fact, there's even a common phrase for this. When something starts twisting out of your hand, you'll say, hey man, that's torquing out of my hand. I don't know if have you ever heard that term? Yeah, that torqued out of his hand. Yeah, it just means that its state of rotation is changing, and so it's being pulled out of the hand, not because it's too much force, but because it's too much torque. It's twisting out of my hand. Okay. Well, let's go ahead and sneak up on this concept of torque. Let's ask ourselves, what does torque depend on? So here I'm going to have 3 identical doors. 3 identical doors. Okay, here's one. Here's another. Here's a third. Okay, and for each of these identical doors, this thing that I put here is the hinge. That's the point about which the door rotates. And I'm going to exert 100 newtons on each of these 3 doors, and you got to tell me which of these 3 doors is more likely to open due to the 100 newtons that I'm about to exert. Here I'm going to exert my 100 newtons right here. On this door I'll exert the 100 newtons right there. And on this door I'll exert the 100 newtons right there. Same force on all 3 doors. Tell me, which door is more likely to open?
The first one.
How many people say the first one? Hey, good for you, right? And tell me, what is it about this force? It's the same force. What is it about this force that makes it more effective in opening the door?
It's doing more work.
What's that?
It's doing more work.
Okay, because it's moving a farther distance. True. Tell me more. I just want you to look at the application of the force. How is the application of this force different from that one or that one?
It's the farthest from the hinge.
Yeah, thank you, Imani. It's the farthest from the hinge. I get the most torque when my force is applied farthest from the point of rotation. And so that's the first fact I want you to know about torque. The farther the force is from the point of rotation, the more torque you get. Here, let me write that in a kind of concise way. More torque if force is applied farther from the point of rotation. Okay, that's the first fact you should know about torque. Has anyone ever had this experience where you're walking towards a door and you don't know which side of the door the hinge is on? And so you choose one side and you choose wrong? Yeah, that's always fun, you know, because if you choose wrong, you just bounce off. You know? If you choose right, you open the door. Now, I guess the safe thing to do, what would be the safe thing to do if you're approaching a door that you don't know where the hinge is? What's that?
Go towards the doorknob.
Well, you can't see the doorknob. You're approaching a door that has no doorknob.
The middle.
Yeah, you go for the center, but then where's the fun in that, right? So yeah, you definitely just choose a side and either you're right or you're wrong. Okay, great. So let me give you another scenario. 3 identical doors, okay? And I'm going to apply my 100 Newton force as far from the point of rotation as possible. So here we go. Here's my 3 identical doors. Here, I'm going to apply my 100 Newton force right there. On this door, I'm going to apply my 100 newtons of force like that. And here, I'm going to apply my 100 newtons of force like this. Now, which of these 3 doors is going to more readily open due to the force that you're applying?
The middle one?
Well, let me ask you this. Is this 100 Newton force going to open this door at all?
No.
Heck no. Have you ever heard that saying? It was a saying popular when I was a kid. Like if you got a black eye and someone says, oh, how'd you get the black eye? But you were embarrassed to say how you actually got the black eye. Then you just say, I ran into a door. Has anyone ever heard that? Okay, a few of you guys. Okay, a few of you heard that. Yeah. And me, when I was 6 or 7 years old, that made no sense to me because in my house, all the doors are ajar. So if you run into a door, you just open or close the door. How would that get me a black eye? So I determined, okay, they must have been talking about this really rare occurrence where you run into the door like this. Because yeah, if you run into a door like this, you get a black eye. And you're certainly not opening or closing it. Okay, so this force, all it's going to do is give you a black eye. So tell me, between these 2 forces, which is going to more readily open the door? I need you guys to vote. How many people say this force is going to more readily open the door? Okay, how many people say this force?
Go with that one.
Okay, well, I'll tell you, it's this force. And someone tell me, why is this force going to more readily open the door? Yeah, Chris?
Because it's put at an angle, so the y component of the second force is going to be less than the initial force.
Great. So Chris is addressing the y component. Chris knows that when it comes to opening a door, you've got two components of force, the y component of force and the x component of force. Is that x component of force helping to open the door? Heck no, all it's doing is giving me a black eye. Only the y component of force opens the door. Well, this is all y. And so I want you to see generally, if I want maximum torque, what has to be the relationship between the door and the force?
Perpendicular.
Yeah, perpendicular. You want them perpendicular. So that's the second thing I want you to notice about torque. And that is you get maximum torque, or rather, let me say this, only the component of force perpendicular to the door opens the door. Only the component of force perpendicular to, and instead of using door, do you mind if I use the proper term, which is lever? This door, actually, we're going to start calling it a lever from now on. And in fact, tomorrow you'll learn about lever arm. But for now, only the component of force perpendicular to the lever rotates the lever. Okay. So I want you to see that torque depends on three things. It depends on how far you are from the point of rotation when you apply your force. It depends on how your force is oriented relative to the door. Perpendicular force gives you the most torque. And finally, of course, it depends on the force, right? I mean, you know, when I'm opening a door versus on an east, let's say, I'm going to be able to exert a lot more torque just because I can exert a lot more force. You know, because I'm a big, strong, muscular, powerful man. You know.
Okay.
Yeah. So, let's go ahead and get an equation for torque. I need to teach you how we express torque, and we don't use a capital letter T because that's for tension. We don't use a small letter t because that's time. So we end up having to use the Greek letter for t, which is tau. But I always use the word torque. I never say tau. I don't say tau equals I alpha for some reason. I always say torque equals I alpha or torque equals whatever. But anyway, that's torque. So the Greek letter tau. And that equals the, let me get my notes so I write it good. It's the component of force perpendicular to the lever multiplied by the distance from the point of rotation to where force is applied. So I want you to see that this definition includes all three aspects. Number one, the farther you are from the point of rotation, the more torque you have. Number two, the component of force perpendicular to the lever is what does the rotating. And then number three, of course, the force itself. The more force you exert, the more torque you're going to get. Well, let's go ahead and boil this down to something a lot easier to work with. What if I had myself this door of length d, and let's say I had a force, and that force was acting at an angle theta. The torque would be the component of force perpendicular to the lever. Well, if the angle between the lever and the force is theta, and this is the component of force perpendicular to the lever, and of course if that's theta, that makes this angle theta as well. You tell me, what's the component of force perpendicular to the lever going to be?
That's cosine theta.
Mm,
Or just cosine theta.
yeah, good. Okay, you guys okay with that? It ends up being F times sine of theta times the distance to the hinge, which is D. And so our book expresses it as tau equals force times distance times the sine of the angle theta, where theta is the angle between the force and the door. Okay. So, there you go. For the rest of the period, for the rest of our time together, I'm going to give you 5 examples, and you guys will calculate the torque for each of those 5 examples, and then we'll be done. And you'll have some time left to hang out and talk and get caught up with each other's lives.
Be happy.
Okay, let's go for it. Force times distance times the sine of the angle. Here comes example number 1. This is a 5 Newton force acting perpendicular to the lever whose length is 3 meters. And I want the torque about point A, where A is the hinge. Please get me that now. Alrighty. How many people here got 15? Yay. And what's the units?
Newton.
Good, Newton meters, right? You got 5 newtons times 3 meters. That's 15 Newton meters, okay? Now, a couple of chapters ago, what did we call Newton meters? What special name did we give those? Yeah, joules. But I want you to see that torque is utterly not related to work or energy or heat. Torque is something utterly, utterly different, so we don't want to call this joules, or people will think that this is work or energy or heat. It's something different, it's torque. So we maintain the units Newton meters. It's like if you ever, any of you are an engineer in the United States of America, and we use for torque in America, we use foot-pounds. You know, we wouldn't use ergs or British thermal units. You wouldn't use units for energy for torque. Torque is force times distance, foot-pounds. That's what we use in America. You know, but in SI units, you would use Newton meters. There's a couple of things I need to tell you. First of all, torque, just like omega and just like alpha, torque is a vector. Torque has a positive and a negative. And ordinarily, tell me, which direction, what kind of rotation do we define as positive rotation?
Clockwise.
Or have I talked about this before?
You haven't talked about it yet.
I haven't, oh my gosh, this class, my bad. Well, I'll tell you. You know how in trigonometry, if you do the unit circle, how this is theta equals 0, and then you go that way to go pi over 6, pi over 4, pi over 3, pi over 2. You know how you do that in trigonometry? Yeah. Those of you who had trigonometry? Well, we use that same convention in physics. So it turns out that counterclockwise is positive in physics land. So any omega that's counterclockwise is positive, any omega that's clockwise is negative. You see what I mean? Alpha is counterclockwise is positive, alpha is clockwise is negative. Same with torque. So now I want to ask you this question. Is this torque positive or negative?
Positive.
Negative.
Wrong example.
Tell me, it is negative. How do I know it's negative?
It's going
Wait,
clockwise.
Zena? No, it's not because the force is going down. You got to give me a better reason than that. Why is this torque negative?
It's gonna go clockwise.
Clockwise.
Yeah, because it's going to go clockwise. And there's no algebraic way to figure this out. You've got to just use your human cleverness. You've got to ask yourself, okay, I'm a stick. Someone exerts a force. Which way am I going to rotate? And by being the stick, you rotate clockwise, that means that that's a clockwise rotation. You can't use up or down or left or right. You've just got to ask yourself, what am I going to do? Do I rotate clockwise or counterclockwise? So in this case, this is actually a negative torque. You guys okay with that? Okay, and then there's one more thing I need to tell you. Why am I telling you that I want the torque about point A? Well, I got to tell you, there are some times that you're going to be exerting forces on things and you're not going to know what point they're rotating about. You're not going to know what the point of rotation is. And your torque depends on where the point of rotation is. For example, this torque is negative 15. But what if I declared, oh, nay, I think the point of rotation is going to be right there, 1.5 meters away from the force. Well, now, what's the torque about point B going to be? What's that?
Negative 7.5.
Yeah, negative 7.5. Is that what you said? Yeah. You see that negative 7.5, right? Your torque, unlike a force, if I'm exerting 100 newtons of force on you, it doesn't matter where I'm exerting it, I'm exerting 100 newtons of force. But torque, where it's applied does matter. You know, if I'm taking my torques about point B, now my torque is only negative 7.5. Hey, let me ask you another question. What if I did my torques about point C? Tell me, what's the torque about point C equal to?
0.
Yeah, 0. Now I'm exerting my torque on the hinge. I'm getting a black eye. I'm not going to be rotating anything. You see? So that's the two things I need you to keep in mind as we use that formula. Number one, counterclockwise is positive, clockwise is negative. And number two, you do have to be meticulous about indicating, hey, this is the point about which I'm taking my torques. Because all your lever arms are going to be measured relative to that point of rotation. Okay, hey, let's do another one. Example number 2. This is going to be easy. 3 meters, 5 newtons, and an angle of 40 degrees. Okay, good luck. Please find me the torque now. Okay. And we want to talk about point A. I forgot to indicate that it's point A. So what'd you guys get? 9.6? All right. Any question or problem on that? Okay. But hey, let's do number 3. Okay, please give me the torque about point A. Good luck. Torque about point A.
Point.
You guys got an answer yet? Wait to see if everyone gets an answer. You got an answer, Anais?
Not yet.
Okay, I'll wait for you. I mean, shoot, you got all the time in the world. You're gonna be done in like 5 minutes, then you'll have 10 minutes left in class to do it whatever you want. Get on your phones and spread rumors about bombs. All right. Hey, you tell me, what'd you get? What'd you get?
9.
9.
9.
9. I don't know what you guys don't like. 9.
I got
What'd you
6.
guys get?
I got
-1?
6.
-1.
Anyone get +1?
No, I got 6.
You got 6?
Yeah.
I got it.
Anyone get like 29? Anyone get 29?
You can quite possibly get 4 too.
Okay. Hey, let's go for it. Noelle, how'd you get 9?
So there's 2 different forces acting on it. So I found the torque from the 7 Newton force and then torque from the 5 Newton force, and they're going in opposite directions. So the 7 Newton force is doing a positive torque, and the 5 Newton force is doing a negative.
Is that the right answer?
Beautiful, right? I mean, the 7 Newton force is doing a positive torque because it's counterclockwise. How do I know? Just because I'm using my human intelligence. And the 5 Newton torque is doing a negative, okay? What's your guys' problem with this? Yes, Justin.
The 1 next to the 5 should be a 3.
What? Why should the one, there, it says 1 right there, Justin. I don't know what your problem
But
is.
it's the point of
I
rotation.
don't know what your problem is.
Oh, it's going to be measured from the point of rotation. You guys okay with that? Yeah, don't make that mistake. Did it sound serious when I said that? Oh, no, I'm sorry. Oh, good, good. Yeah, just joke, Justin, come on, man. Yeah, you guys okay with that? So I'm just very lucky that Noelle happened to make the mistake that I was trying to trap you guys on. Always be mindful. All of your torques are measured from the point of rotation. It's so important to know what that point of rotation is because that determines what your torque is. You know. So yeah. So you guys see that it's -1 Newton meter. 6 Newton meters. How did you get that?
Oh, me?
Come on,
6?
yeah.
Whoa, okay. So I subtracted like the 7 and the 5
Oh.
because it's gonna go up, and then I multiply it by the distance.
Cool. Yeah, yeah. Unfortunately, your torque has to be the sum of each individual torque. There's no quick way to do it. Yeah, it's not like force where you can just add up all the forces. Yeah, I'm glad you made that mistake too. Okay, guys, you ready for another one? Here it comes. I'll have both my forces pointing the same direction this time. See if you guys can figure this out.
Thanks. Oh boy.
Okay, please give me the torque about A. Good luck.
That was mean of you.
That was.
Huh?
She's emotionally unavailable. What did it? You're emotionally unavailable. You don't care about any feelings.
Except my own. Don't hurt my feelings.
Can I just wait for you to do it? I'm tired of crossing stuff out.
Oh, you're using a pen.
Alrighty, so what'd you guys get for this? 20. How many people got 20? Positive 20. Okay. Noelle, you didn't get positive 20?
Yes.
So, someone explain to the class, how do I get 20? What did you guys do? Want to explain it? Yeah, Cole?
Well, I visualized it like a door, so I imagined that if you pushed on the left there, it was the bottom, the right side would go down.
Beautiful.
So they would cancel each other out. So I treated it basically like the previous problem where I treated them as two opposing forces. So I subtracted them, and I got 20 Newton meters.
Okay. Now, did you get each individual torque?
Yeah, so I
this
did
one-
15 times 2, and then
Good.
10 times 5.
Beautiful. Good. You guys okay with that? He recognized that this is a negative torque and this is a positive torque, because this torque will tend to rotate things clockwise and this torque tends to rotate things counterclockwise.
Does being to the left of the point of rotation matter at all?
Well, yeah, and it only matters because in your mind's eye, you have to picture, okay, what is an upward force going to do to this thing where the point of rotation is to the right? And that's going to do just what Cole said, it's going to rotate it like that. And you're going to have to use your human cleverness. There's no other way to do this. I can't teach you an algebraic way to make this determination. One exists, but I'm not going to teach it to you. It's using vectors R cross F. Torque equals R cross F is the way you're going to learn it when you go to college. But you don't know what cross products of vectors are, and don't even worry about it. So you're stuck doing it this way, and that's okay. 15 newtons times 3 meters plus 10 newtons times 5 meters. So I get torque equal positive 20 newtons. Okay, well, hey, here comes the last one. This one's going to be pretty easy. Here. 60-degree angle, 8 newtons. This is 8 newtons. 10 newtons at a 45-degree angle. This is 2 meters from there to there, and this is 2 meters from there to there. And remember, this is your point A, so all your lever arms have to be measured relative to point A. Good luck. 45-degree angle, 60-degree angle. I gotta make my 10 a little bit longer than my 8. So what you guys getting?
14.4.
14.4?
Oh, wait.
Noel, did you get 14.4? So I couldn't fake you out again on that one? Yes. Because it's so rewarding. Any question or problem on this? That's what you're going to be doing on tonight's homework, man. You'll just be getting torques. Tomorrow we do more. Tomorrow we do free body diagrams, but tonight just get torques. Good luck. Bye.